molecules are sufficiently far apart because it's an asymptotic expansion. And then you might make a very normal and understandable mistake that you think, aha, this is the extension of the molecule, and the extension of the molecule, let's call it Rm, must be much, much smaller than the separation of the two molecules. This is not true. Because what only is necessary is basically that the effective extension, and that's basically the size of the dipole, is much smaller than the separation of the molecules. Yeah? And there's again an analogy to optical absorption in electromagnetic field. So we also make the dipole approximation there, which requires that the wavelength of your radiation is much, much larger than the size of the atom. And this is also not true, because the wavelengths must be much larger than the size of the orbital which absorbs the photon. And this can be very small. For instance, if you go to X-rays, yeah, where then the wavelength is very short, and you think, oh, now I'm in trouble with my dipole approximation, because the size of the atom might be even larger than the wavelengths, you still can apply the dipole approximation. Why? Because X-rays, because of momentum conservation, what I told you yesterday, where does the absorption take place? Very close to the nucleus, yeah, for high frequency, short wavelengths. You actually have very, very tightly bound electrons which are susceptible to this X-ray radiation, and the extension of this orbital is very small. And then the dipole approximation is again okay. So that's very similar here. The effective size of the dipole matters in relation to the separation of the two molecules. Okay, this is described here again. Okay, now let's talk about the minimal aggregate, the dimer, 2 units, and discuss first the ground state energy. So here are now my two charge distributions with the dipole. They're separated somehow, and that's now very simple. I assume that each of these molecules has only 2 states, yeah, the ground state and the excited state. And in the end enumerates the molecules, molecule 1, molecule 2, and 0 is the ground state, the upper index, and 1 the excited state. And now we make the most primitive perturbation theory you can think of. Well, it's not totally primitive because it's degenerate if the molecules are identical, but other than that, it's really, really very simple. And the ground state energy is then simply given by the Hamiltonians, individual Hamiltonians, plus, of course, the interaction energy I showed you. Yeah? And the expectation value of that was simply our product wave function from the 0th order. So both molecules in the ground state. It's very easy to evaluate that. Of course, individually, this just gives the isolated ground state energies, and this is the interaction energy. It's called E00. Yeah. Okay. And so that's the ground state. And what is important to see that the ground state of this interacting 2-unit dimer system is a little bit different from the sum of the 2 individual ones through the interaction energy. And in general, it's redshifted. So actually the total ground state energy is lower. Why is that? Why is it not higher in general? Because you have more Hilbert space available, more volume where your electrons can settle through the interaction. Yeah? Now the excited state is now, and this is already our excitonic concept. Yeah, we have a single excitation. That means we can either put the excitation into our molecule 1, and the second one is in the ground state, or the other way around. Molecule 1 stays in the ground state, molecule 2 is in the excited state. And then we have a linear combination. Let's say we write a very primitive basis. Yeah, this is molecule 1, molecule 2, here's the excitation, here's nothing, and the other way around. And of course, you have the coefficients, and now you can diagonalize essentially your Hamiltonian matrix in this basis of having these 2 basis states. And if you do that, then you get the normal Schrödinger equation with the same, of course, operators, the individual Hamiltonians and the interaction energy, and get the new energy. And to get the new energy, you know how to do that. You have to essentially take the determinant, yeah, of this matrix, and here is then the matrix element, the diagonal one, with the 2 individual energies and the expectation value of your interaction energy with molecule 1. That's the energy you're looking for. Here's the same thing with molecule 2, and this is the interaction energy between the 2 molecules, and since the whole thing is Hermitian, we know that this must be the same or complex conjugate It's like yesterday, 2x2 coupling. So here it's real, that's identical. And since we use, for now, identical molecules, of course, V11 is also V22, but that's not necessary for the formalism. Here you see again the matrix elements. That's really very, very simple. So nothing magic here. So now we can calculate that. And you can do that, of course, analytically. You know how to solve a determinant, right? This times this minus this times this is 0. So this is basically the same because 1, 1 and V22 are identical. So this gives us 2 times the same thing is squared. And here this is also identical, is this one squared. And now we can solve that for the final energy, which gives you, of course, 2 different solutions. One is basically the lower one, it doesn't matter which one you take. The individual energies of the isolated molecule, the interaction energy with molecule 1, plus V12, and the same thing, minus V12. So you see, this is kind of maybe expected that, yeah, you get a splitting of which is proportional to the interaction energy, but you also get a shift with the diagonal matrix element here, the V11. And this I tried to show here again. You see this is the energy axis, and here we start out with our non-interacting system, so the 2 isolated molecules. And we know in the ground state they have like the ground state energy, which we here put simply to 0. I mean, you can of course choose whether 0 of energy is, this doesn't matter, and we're not interested in that. And then the excited state would be degenerate, right? Because the molecules are identical. Molecule 1, molecule 2, without interaction have the same energy, epsilon 1, that's here. Now we let them interact. First of all, the ground state, remember, has this interaction energy, V0, 0. So that's not just the sum of the V0, so this is lower. In general, it will also be higher, but in general it's lower. And now, of course, the interesting thing is our excited state, that's what we're doing here, gets split. Here was degenerate, and we get these 2 solutions here. And we know they are basically splitted by 2 times the interaction energy, which is called Davidoff or Exciton splitting. And another important energy difference is the one which goes basically to the average of the excitation level here. And this average, I told you, if you add these 2, is shifted by V11 with respect to basically the non-interacting excited state energy here. And this is, again, not really the energy difference to the interacting ground state, because the interacting ground state is lower here. Yeah? So, therefore, this energy is not totally trivial. This difference between the mean excitation energy and the ground state energy is given by V11 minus V00, and this is called displacement energy. And why is that important? Because in the experiment, of course, you don't observe energy levels, you observe energy differences and absorption spectrum and so on. And that is really appears shifted, these bands, and shifted also through this ground state energy here in the interaction. Okay, now this is relatively simple now. It follows that your coefficients are almost all the same, just with a different sign. And these 2 solutions have now these eigenstates in terms of the unperturbed linear combination of our molecular wave functions. And you see, of course, what we had before as an ansatz with coefficients here and here is now a perfect symmetric or antisymmetric linear combination, which means your excitation is completely delocalized on the 2 molecules. Fine. Now, what are generalizations? I will not discuss with you. Here is relatively simple. Of course, you can have non-equivalent site energies. That means even for identical molecules, in a realistic situation, the site energies might be different. So epsilon 1 is not the same as epsilon 2 due to the environment of these molecules. Yeah? But this is very easy to incorporate. Essentially, here you don't have a degenerate level, you have 2 of them, and these 2 energies get a little bit modified, but essentially you still have a splitting, and qualitatively everything remains the same here. You can include more excited states. This gets already a little bit more dirty, of course. And of course, lattice vibrations will change. Essentially, your picture will broaden also your peaks and so on, the absorption spectrum. And you have not only lattice vibrations, but in general, quite a few broadening mechanisms. In general, they are related to the scattering, or you can think of it, these broadening mechanisms, as scattering of the excitons from all kind of different perturbations. Okay, let's come very briefly to transition dipole moments. This is what we discussed yesterday. Photo absorption is of course related to the dipole moment, so we can do that here again. So now the interaction Hamiltonian for a single unit is just the electric field times the dipole moment of our molecule. Still the same dipole moment I've been discussing all the time, right? The red arrow from a charge distribution. And yesterday we called basically what's called mu here now d, yeah, in the velocity gauge, just to remind you. And then the transition rate, again simply by Fermi's golden rule, is given like that. And what is important is that basically it includes simply the direction between the electric field and the direction of our dipole now for the molecule. And this we call the transition dipole moment. So that plays a very universal role in all these molecular aggregates, and we can express later on the dipole-dipole interaction energy also in terms of these transition dipole moments of the individual orbitals, yeah, of the different units. Clearly, if you have an isotropic sample, then you average over everything and you get 1/3. That's trivial. So now let's come, which is already a little bit more interesting, to the absorption of an excitonically coupled dimer. So that's what we just did, right? We coupled these two molecules together. And now let's see how the absorption changes compared to the individual absorption of these units. So our ground state is as before, the excited state is also what we had. And we can define the transition rate simply from the ground state to the excited state. Now our interaction energy is the transition dipole. This is the electric field times the individual dipoles moments here. And as I said, this can be really formulated very easily here in terms of these individual dipole moments, which are basically matrix elements of your orbital of one molecule in the ground state and the same molecule in the excited state. And then it reads like this: linear combination of these two transition dipoles of molecule 1 and 2. And we know that we have these two different excited states. We just calculated them, right? Separated by the splitting. So if you calculate now the total absorption strength, you sum over all the states available, which are 2 in this case, excited ones, split it by the Davidoff splitting, then you get essentially the dipole absorption strength like that. And if you insert your solutions, then you find that in the two solutions, 1 and 2, you get basically this kind of absorption strength. And this is very reasonable because it is parameterized essentially by the angle these two dipole moments form in our coupled dimer. Yeah, this basically tells you how strong the absorption is. But, and this is now very interesting, here the D is the individual identical dipole strength, yeah, again the orbital, the transition matrix. And what's very interesting is that, of course, the total strength, if you sum over all possibilities, does not change. You see that directly here. If I add D1 and D2, the dependence on the angle cancels, right? This is plus and minus. And the sum is just 2D, just twice the individual dipole strength. And this is the same as in the unperturbed, isolated two molecules. And that's a good lesson to take home. Essentially, the total dipole strength, it's all these oscillator sum rules, is independent of the interaction. Yeah? And this is also true if you go to, let's say, a large system with n molecular units, then the total strength is n times d. Although the individual, of course, absorption strengths might vary dramatically in the different excited states. But if you sum over all of them, then you get just n times the individual one if you had n molecules. So I think almost done. Yeah, I should be almost done. Dipole-dipole coupling. Now we come to what we are more interested in. For transport, in terms of individual dipoles, again these orbital dipoles, yeah, I will always take these orbital dipoles, don't forget that. Where are they? These ones, yeah. And this is now the same here. So now we are dealing with this matrix element we are interested in. These are the operators still. And here's one molecule in the ground state, one excited, our typical configuration, and the other way around. So something happens. And of course I can do the matrix element and then express that again in terms of these numbers, which are already the transition matrix elements of the individual dipoles for molecule 1, molecule 2. These are vectors, and here also. But now, of course, they are projected onto the basically axis between the two charge distributions. You can express it formally like this, over r to the cubed, proportional to the individual dipole strength again. But the kappa is now this expression here. It's the cosine between the two dipoles minus this term. And you see this can have dramatic consequences. For instance, if you arrange your two molecules in such a way, parallel along each other, then the dipole moments are parallel to the distance vector, if the center here is basically the distance, measuring the distance. And that means if you calculate that your interaction energy is minus 2 times the dipole moment. Dipole moment is of course the same, it's identical molecules. Now if you arrange it in that way, like a sandwich, then the distance vector is perpendicular to the dipole moments, and that gives you of course a very different contribution here. Now all of a sudden your dipole moment is mu squared. Yeah, and not minus 2 mu squared. Which is maybe in the first glance not very intuitive. Yeah? It's almost counterintuitive because you think, it points into the same direction and so on. No, but it's really the projection onto the distance vector which matters here for the interaction energy, and therefore the strength is really, really different. Okay, so this is an illustration. Sorry for the bad quality. I took that with the iPhone this morning from the book. But how this really happens, that's from the book I advertised to you. So this is a true light harvesting unit, FMO complex. Don't make me pronounce that here. It's not for physicists, at least not for theoreticians. So, but what I wanted to illustrate to you is really, this is very, very complicated, huge systems. Many, many, many molecules and atoms contribute to one unit. This is one unit, one molecule here. Oops. And, I think this just died on me here.
Good timing.
Good timing, right. And here are the dipoles. So this is dipole of molecule 1, dipole of molecule 2, 3, and so on. So they really, but this is real. This is measured. This is how it is. Yeah. And you see they have very complicated interaction energies and so on. And people also then really measured or tried to extract from measurements and calculate here the site energies. They are here on each of these units I showed you relative to some reference line. And also the interaction energies between these different dipoles here. They are all listed here, and from that you can then try to calculate your absorption spectrum, and you will find it does not agree with the experiment, but we want to have something to do in the next decades, so that's okay. Alright, so in larger systems, everything goes more or less as we did for two systems. For two units, now let's say we have a chain here, yeah, of our molecules along one line, periodically, yeah, but the dipoles can point wherever they want. Then we have this big matrix now, where all the molecules sit with their site energies, and the interaction energies individually always between two of them, with their 1 over r cubed distance. And now we have to diagonalize this big matrix. This gives, of course, a vector. And the excitation energy is again the individual one, which is assumed to be the same, because they are identical molecules. Plus the shift, you already know, this V00 or V11 for two ones. Now, of course, it's summed over all the possibilities, yeah, the shift. And now the basically off-diagonal interaction energies, and that's not so trivial, that's the interesting part, because here now comes this periodicity in. Yeah? Since this is periodic, it must be modulated with a phase factor here, E times K times M, which is the Fuchs vector, which runs through all the units. And that's then, of course, here proportional to the interaction energy between two individual members, this and this or whatever, M and N. Yeah, so the result is now, and that's almost the last thing I do, if you have now a linear finite aggregate with 3 edges, so in the end there's nothing, then you get coefficients on each of your orbitals here like this. This modulation of the energy looks like that, and now one does something which is very common. One makes a nearest neighbor approximation. One says only basically pairwise these things interact, and then this collapses to a very nice closed form, J times cosine pi j n plus 1. So that means that basically the individual energy levels, of course it splits now n times, right? And the United States for 2 units has 2, 1, now it has n times. It's just distributed between minus j and 2j, discrete, depending on how many you have here. And again, the center is shifted with this overall interaction energy, but this is now our exciton energies. And these are the exciton energies we will start with tomorrow for our Rydberg arrangement of atoms. Same thing. Yeah? Just as regularly spaced Rydberg atoms tomorrow, and they have the same energies here in their exciton excitations. And I think this is more or less, yeah, what I wanted to remind you. I will do that tomorrow, and we'll show you. I think it's tomorrow. It's after dinner, so there will be some movies, and maybe I should have told you about time tomorrow after dinner. But anyways, thanks for your attention. Yeah.